Okay, so I think that we can go. Okay. Okay, so that's a pleasure to have here my colleague and friend Ahmed Sebbar. When we discussed the MPP seminar, the question was about the format on the seminar, and what my colleague said is the essential difference between a physics and mathematics and the philosophy seminars, that physics in 45 minutes, mathematics is 1 hour, and philosophy is 2 hours. So now we will see whether Ahmed is a physicist, a mathematician, or a philosopher. We can see with him. I think that it will be something between mathematics and philosophy, more or less. We will see. So of course, so we have 2 hours, perhaps a little bit less today because there is Magic Johnson that I want to see. So I cannot lose Magic Johnson at 6 o'clock. So a 5:45, I have to leave myself. You stay as you want, but I have to leave. Okay, so the congruent number problem, 1,000 years of 1,000 years story. So Ahmed, I don't know whether you accept the idea that someone can interrupt you to put question, or you want
absolutely, yeah, absolutely.
So feel free if you think that is
except if it is not.
Except me, all of you have the right to put questions. Ahmed.
Yeah. Okay, thank you very much. I would like to talk to you about the story of some numbers. And we know that numbers have been always important for humankind. And I would like to talk about some strange numbers. Numbers have been very important for Diophantus. We have here the cover page of his book, the edition of 1621. And there are always some strange numbers. You know the taxi cab 2. You know, this is a story of Hardy wanted to visit Ramanujan in the hospital, and he took some taxi, and the number of the taxi is 1729. When Hardy entered the room of Ramanujan, he said, I don't like this number because it is the product of 3 prime numbers, and the difference between those 2 prime numbers, each 2 prime numbers is 6. I don't like this number. But Ramanujan said almost immediately that this number is very interesting because it is the first number that can be written as sum of 2 cubes in 2 different ways. And this is what we call it taxi cab 2, because it is written as sum of 2 cubes in 2 different ways. And we have to wait a long time. We have to wait 1957 to find taxi cab 3. That's a number that can be written as sum of 2 cubes in 3 different ways. And of course, here I'm taking positive numbers. When we take negative numbers, when we accept negative numbers in the cube, then we are speaking about cab taxi numbers, which are, and here the numbers can be smaller. So the numbers that I'm going, before that, algebraic equation in the book of Diophantus, algebraic equations were very important. And the theorem of what we call the rational root theorems is very, very old. And it is a way to check if when it is possible that some rational numbers is a root of some algebraic equation. And if you take this rational number in the form of P over Q, with P and Q co-prime, then necessarily P should be a divisor of the first, the last coefficient, and Q should be a divisor of the leading coefficient. This means that, for instance, if we have a cubic equation, something that will be important for us in this talk, it is very, we have A and D, and then we can look at the prime divisors of A and the prime divisors of D, and then you make some small check and to see if our rational numbers P over Q with P and Q co-prime is a root or not. In any case, when it is a root, it gives us a better method than Cardano method, because the Cardano method, and here I just put it in the form of small history. There is this Tartaglia poem that give you the Cardano method. The problem with Cardano method is that it gives cubic roots, and sometimes you have very big sum of cubic roots, and this big sum of cubic roots is just 1 or 2 or 3. So this rational root theorem, sometimes it is very convenient theorem. And the numbers that I want to discuss, and this is the main point of my talk, is there's sequence of numbers that started with 5, 6, 14, 15, and so on. And I put in red 57 because it is not in the list. And this list of numbers. So
the list of numbers is by Alazen?
Yes.
And
it is in
the red one is added by you.
No, the red one, it is not on the list. It's not by me, not by me either. I'm going to talk about this. So this list of numbers exists in some manuscript at BNF, the French National Library, and there's numbers. I don't really understand how Alazen write to those numbers. In any case, Alazen, and the true name of Alazen is the Latinized name, and the true name is Ibn al-Haytham. It is in 1972. And this mathematician, actually he was a polymath person, is considered by, here I gave some names, Newton, Kepler, Descartes, Huygens, Galileo, as the father of the geometric optics. And here you have the book of optics, and here you can see this is of, I think, the 15th century or something like that. And here on the right, you have a copy of a page of the original. In any case, Alazen was really, he was the father of the geometric optics, and there are a lot of theorems on planar geometry, on triangles, and why he wrote this list of numbers, I don't know really. But in any case, at that time, Alazen also was in contact with another mathematician. And let me just give you a definition of what we call amicable numbers. So there are two integers, and what they are called amicable if n is the sum of the divisor of n, but less than n, and n is the sum of the divisor of n and p less than then n. There are amicable numbers. And around then, there is another mathematician who is called Tabit. And now, if you look at Wikipedia, you will find what is Tabit number. And Tabit wrote a criterion how to construct amicable numbers by defining what we call Tabit numbers, 3 times 2 power n minus 1 minus 1. So this criterion shows that, for instance, the smallest couple of Tabit numbers are 220 to 84. This is when we take n equal to 2 in the formula given by Tabit theorem. And for n equal to 4, we have big numbers and so on. So there is some...
A perfect number is amicable of himself.
Then after that, Fermat took this definition and put it further. Fermat and Mersenne and so on. So this is the story around those numbers. And I gave here a picture of a definition. First, I gave a definition of a congruent number. What is a congruent number? A congruent number is some integer which represent the area of a rectangular triangle with rational coefficients. So this is what we call a congruent number, and I will come soon to the motivation of the definition of this congruent number. And I put 157 in red in my list. It was not in the list that I gave you before.
Also have to be rational?
Yeah, absolutely. Yes, thank you.
Okay, otherwise, okay.
Yes. With rational size, the 3 sides. And I put in red 157, and Zagier gave the side of the triangle with area 177. And if you look at the denominator, we have 22 digits. It is something that you can do by hand. It is Zagier. Well, I think it is not so old. Well, Zagier is really very involved in this theory. Maybe I'm sure that it should be after 1980. Very early. So
that means that A times B divided by 2 is equal to 157.
Yes, and you have the square of the first plus the square of the second. So with the square of the C, A square plus B square equal to C square, which is not trivial at all. So the story now in 1225, Frederick II, and I recall that Frederick II was the emperor of Sicily, Italy at that time, Germany, and Jerusalem. And this emperor liked mathematics.
Was the president?
Was?
Was the president?
Yes, and he liked mathematics, and he organized some kind of Olympiad of mathematics, and around him, there was a young mathematician, Fibonacci, and he asked Fibonacci to answer some question asked by John of Palermo. Here I have a question for Marco to explain to us at the end of my talk, who is John of Palermo? John of Palermo is a very mysterious person. I can talk to you about this. And he asked, and the problem asked by John of Palermo to this group of mathematicians to find 3 squared rational, and the difference is 5, which means that, we will see this later, to give a proof why 5 is a congruent number. The question of John of Palermo is to find 5 squares of rational numbers, A squared, B squared, C squared, such that A squared minus B squared or B squared minus A squared equal to 5, and the C squared minus B squared is equal to 5. And squared, they are squared. And they are squares. And of course, Fibonacci gave the solution of this problem, and as tried to replace 5 by general number, and he gave some, he called congruent numbers. This difference here, Fibonacci called this difference congruent, and this was the origin of congruent numbers. And the proof that he gave for the general problem was not satisfactory. And it was 200 years or 300 or 400 years later that Fermat proved that it is impossible for a right triangle with side all integral to have area equal to 1, which means that Fibonacci proved that 5 is a congruent number, but he was not able to prove that 1 is a congruent number. And it was Fermat who proved that 1 is a congruent number. So my talk today is to relate this to a famous contemporary big problem in mathematics, the conjecture of Birch and Swinnerton-Dyer. Here you have the picture of, on the left, you have Swinnerton-Dyer, and on the right, you have Birch. And this photo was taken maybe at some celebration. I know what the celebration is, but it is not necessary to enter in. So this conjecture that we call BSD, Birch and Swinnerton-Dyer conjecture, is the main point of my talk. And this idea is, in some sense, to relate local problems to global problems. In roughly speaking, when we have problems with rational numbers, in general, this problem is difficult. And then what we do, we look modulo prime numbers. For instance, if you have a rational number, this you can always write it as 5 modulo 29. So when we think periodically, we can reduce rational numbers to integers. This is the idea that we are going to develop. So the idea of Fermat to prove that 1 is a congruent number is to use the method of descent. And this method was already in Euclidean elements, proposition 31 in book 7, but Fermat pushed the method further, and he proved in particular that the Dyer-Fontaine equation are square plus to have light here.
Oh, it doesn't show on the screen.
To show that the Dyer-Fontaine equation R squared plus S4 equal to T4, it has now no solution in integer solution. And the main point, and here I arrive at one of the, I can't stop admiring this result, that when you have a prime number, P, and that P can be expressed as sum of 2 squares when P is equal to 1 modulo 4. And this is the main ingredient in the proof of this kind of result. We will come on this later. So now if you take a congruent number.
I do not understand what is the conjecture. What's the conjecture?
Oh, yeah, we have.
You still did not say this.
No, no, no.
Okay.
No. I'm coming to the conjecture. So we have problem in planar geometry, and now we are going to construct elliptic curves from this planar geometry. So we assume that n is congruent number, then we can write c square equal to a square plus b square, and we have 2n equal to ab. So we have a square plus b square equal to c square, and then we have that the area is equal to n, which means that we have this. And from here, by simple manipulation, I'm going to add and subtract something, and we arrive to very elementary manipulation. We arrive that if we have some rational number verifying this, then we arrive at the following, that the curve minus n squared should contain rational point. So if you have rationals verifying this condition, and this n is the n squared that I have here, this curve, I'm going to give you a picture of the curve, should contain rational numbers. But before this, let me just show you that, for instance, 6 is a congruent number, because if you take 4 and 3, 4 and 5, we find that the area of this rectangle is 6. But there is no uniqueness of the rectangular triangle. You have infinitely many. This is coming from later. And here you have some other rectangular triangle having the area equal to 6.
What does it mean that contain rational point? Does it mean that there is one point in the curve, so was coordinated with
rational? Yeah. So here I wanted just to show you that the triangles become more and more complicated, but they are infinitely many. Here I arrive to what I call by rational points.
I don't quite understand. X equals 0 and y equals 0 should always work, but it is not interesting.
No, I'm not interesting, because we take area here. We want because the dictionary between this A, B, C, and this should be, the rational point here should be no 0. Yeah. Let me just look at the simple example of the circle. We consider that the simplest curve are the line and the circle.
So n is not a congruent, 0 is not a congruent number.
No, we don't consider 0. Yeah. So when we have a circle,
Mathematicians are strange people.
when we have a circle, why the circle contains infinitely many rational points? The situation here is very easy. I take a line of slope t, and the t is rational. And then this line will cut this point here, which cuts the circle at the point of coordinate 1 minus t2, this classical trigonometry, and 2t divided by 1 plus t. And then we move t, and then we have infinitely many rational points on the circle. We move the slope, and we have many rational points on the circle. Then I can consider the circle and the rational point on it. and I have a low group. Low set of rational points of this circle form a group, an abelian group. But to understand this, why the unit circle is a group? Of course, you can say that if I take θ1 and θ2, then the product is θ1 plus 2. But this is not good for what we want, because this use coordinates. One way to see that it is group, here I have 1. I'm going to read the low group differently. I take this segment, and if I draw a parallel from this point into segment, automatically I arrive here. So I can define the low group by considering one point M1 and not using any more the coordinate, and M2, and I take the parallel going from this point, and where it touches the circle, I call it M1, M2, and I have the low group of the circle. So this low group, why it is associative? And I can do it for the ellipse, and I can do it for the hyperbola. When it is associative, and here we use this Pascal theorem. A Pascal theorem says that when you have an hexagon inside the circle, and you construct the parallel between opposite sides, then where they meet is on a line. The red points are the intersection point of the parallel on opposite, constructed on opposite edge of the hexagon. And this is Pascal theorem, and this gives you the associativity of the low group. The low group is coming from projective geometry. So, and this Pascal theorem can be given for the ellipse, and can be yes, and it has a different interpretation. It can be called Pappus theorem. All the theorem of projective geometry are equivalent in some sense, and it is a particular case of what we call Poncelet theorem. Let me just give you what is a Poncelet theorem. For in simple situation, because this is also will have analog for elliptic curves. When you take a circle, and you take a concentric circle, and you take one point here, and you describe the tangent here, and you take the tangent here, and let me take general picture. I take circle here, and I draw the tangent. And I continue like this. Poncelet theorem says that is this process closed after some number of steps, starting from one point, it will close starting from anything. If it doesn't,
I do not understand the way.
you start from here. You start from here.
And you come back here after.
And then you turn. If after some number of steps you come back to N0, this is what I call close, then this process will close starting from any point of the circle. If it doesn't close at N0, it will not close for any.
For a given internal circle or for any internal circle?
For any, if you give some configuration.
No, I mean, now you have two circles, one internal to the other.
Yeah.
And you see that starting from N, the process closed. And then starting from another point in the same circle and in the same small circle,
For the same circle.
but now I take the same circle and a small circle and display the same circle. Does not mean that it's closed.
No,
So
no, no.
that's
It
the
depends
same
on the
pair of
position, the
circles.
configuration, the position.
Okay.
This is and this theorem is very, very, very important. Now, I go back to the circle. I have group, the group of rational points. This group, I can, we have our group, and what is interesting for this group, it is a abelian group. And we have fundamental theorem of abelian, finitely generated abelian group. And for some reason, this group is finitely generated. And now I use this theorem that if P is prime, and if P is equal to 1 mod 4, then P can be written as 2 squares. And that's 2 squares, the couple M and P, NP and NP are unique up to the position and to plus and minus sign. But this decomposition is unique if I ask in advance that NP is greater than NP. In any case, NP can't be equal to NP because P is prime. But if I prescribe this condition here, then this NP and NP are unique. And then this.
I do not understand the relation between this and the constant theorem and the question of the.
Yeah, I wanted just to tell you that the group of rational points has very precise algebraic structure. Okay. This coming soon, and this theorem is this. The abelian group of rational points on this circle can be written as product, I put plus because we have abelian, as product of cyclic groups. And one cyclic group C2 is of order 4, so this is a small one, and the others, CP, are generated by the point NP squared my NP squared over NP squared plus NP squared, and 2NP NP over NP squared plus NP squared, which are the coordinates. And this comes from, and P describe all the prime numbers equal to 1 mod 4. So the prime numbers equal to 1 mod 4 give you some cyclic group generated by the coordinate for the long group of the circle, the rational point, and give you the structure of this. So the group of rational points on the circle has decomposition into cyclic groups. One is finite and the other are infinite. Now, we can do this, the same thing for I will come on this later. And here we arrive to, I told you that when we ask for the problem of congruent points, we arrive to this curve. Now I'm going to just to simplify the presentation, take n equal to 1. This is the fundamental curve. I'm going to understand what is this curve. And now to go from here to here, this is something that we call the switch. And here I have the graph of the curve x3 minus x in the top. And the low group is exactly the same as what I did here for the circle. I take 2 points on the curve. I take 2 points on the curve, C1 and C2. I drop, I put the line C1, C2. It touches the curve in this point because the curve is of degree 3. So we have 2 roots, so we should have a third root. And what I call the sum of the point of the curve is the Xi1 plus Xi2. So I use the process of force to construct the log of the group. And this for this curve, and now we have abelian group, and we are going to say something about this abelian.
Sorry, can you come back? So these are the two portions of the curves.
Yes, this curve has two components.
Cut the axis in place, so it means that these are always three.
Yes, because we have cubic here.
Yes, but we have here three real. If n is congruent, these are real.
No. Rational points.
No, but if I cut the axis,
Yeah,
in 3 points, so it means that I have three. Y is 0 3 times. So we have three.
yeah. Y is 0 3 times here, huh? 1, 2, 3.
Okay, so it means the equation x3 minus n2x equals 0 has always three real roots.
No, I'm not saying. I'm not this. I'm saying this. I look at the set of x and y in Q times Q, solution of this equation.
Yeah.
This is what I call C of Q, and this is group. I'm not looking at the Riemann surface given by this. I'm looking at this as plane curve, found in the plane, and I'm looking at the set of rational points x, y, solution of this equation. Now I would like to come. What we have to do, we have to maybe I will switch. I will skip this point here. We don't have time. And now we wanted to look at the rational points on this curve, and we wanted to discuss the number of these rational points, and this is difficult. But when we have the general form of this elliptic equation is this. And we take every rational every integrals. And we want to know the number of the solution, rational solution. So this is difficult. What we do, we are going to reduce modulo P and then to work in Z over ZP. And now we are going to look for solution for a couple of solutions XY in this field. So this X can take P value, but EX squared plus PX plus each will be squared. How many squares we have in Z over P? We have we have the half P over 2. P minus 1 over 3. But now, for each solution, we have two solutions. Plus or minus, because the square of y should be 1 of the P minus. So you have two solutions for y. So we multiply to have the total number of solutions. We can guess as that the number of solutions is P. Then we are going to consider, we are calling the right number as P. The guess is P or P plus 1, and we are introducing the error term. So this is the error term. And this is a fundamental theorem of Hasse that this error term is less than 2 square root of P. So this is really a big theorem of Hasse, but it was But the original question was asked by Artin. I put on the left Artin and on the right Hasse. And now, if you look at this expression here, so you can write 80 divided by 2 square root of p. This is in the interval minus 1, 1. And then we can write it as 80 divided by 2 square root of p as the cosine of theta p. And theta p is sum only between 0 and pi. So we don't know the coefficient, the error terms. We don't know them explicitly, but we know that they are given by theta, the cosine of theta p, and it was conjectured by two great mathematicians, Mikio Sato and John Tate, and they conjectured that this sequence is equidistributed with respect to this measure here. And this is really what we call the Sato-Tate conjecture. The theta, I recall that with this if I take sequence in, for instance, the interval 0, 1, and we say that this is distributed, this is not the true definition, but this is a theorem, is when I consider this is the definition here, the equidistributed. This is, I wrote it here. Limit, if you take an interval, alpha, beta, and you look at the number of theta p in this alpha, beta, divided by the total number, and you take the limit, it should be equal to the integral from alpha to beta to this. This is the meaning of this sentence. And we have to say that the sign, this conjecture of Sato-Tate was proved by Taylor and others. Maybe I put the names. No, I didn't put the name. And it was really use some Lie group technique behind this measure. This measure here comes from the hash measure, the hard measure of the group of some special Lie group. So these theta p are not super distributed in the interval 0. We don't know them explicitly, but we know that they are a little bit well behaved. So I said that for the simple, the rational ones can be written as product of cyclic group. We have one small group of order 4, and the others are infinite cyclic group. This is for the simple. But now for elliptic curve, we have a big theorem, Mordell, that if you take elliptic curve and you take the rational ones that I call E of Q, the set of x, y in Q times Q such that the solution is satisfied, it is also can be written as, it is written here, that E of Q, the set of rational ones, is the product of, because it is an abelian finitely generated unit, and it is the general theorem of finitely generated abelian group. It is written as product of cyclic group, but in this case, we have some number of infinite cyclic group, and we have some finite group that called the torsion group, and this is finite. And this are
this for all elliptic.
yes, for all elliptic curve.
So independent of the value of n.
No, for all elliptic curve of this form.
Oh, okay.
For the elliptic curve for x3 minus x, this here, we don't have this part. We have only this. And this, we have only the torsion part. We don't have the intrinsicity part. And this is the reason is that one is not a congruent quantity element. So this is a general term. And this R is what I call the rank of the elliptic curve. And please remember this name. Everything is the rank. When the rank is 0, like for this x3 minus x, we have only the torsion group is Z2 times Z2, which is very small. So this rank is very important. In general, for any elliptic curve, this torsion group is not so big. And we have not so big. And it is of order at most, it contains at most 6 of size 16. Contain at most 16 elements. So, well, this is, I can skip this. And now we have theorem relating congruent numbers to this R. So the theorem is this. There are rational right triangle with area D if and only if ED of Q is infinite. What is ED? So this curve equal to EN, and the N is the one here. And ED is when I put D here, and the D is the area. So so the link between congruent numbers and elliptic curves is this. D is the area of a congruent, number, is the area of a rectangular triangle with rational coefficients, if and only if this R here is positive. Is this the main, and one of the main states is positive? Yes. Which means that the rational point on the elliptic curve is not reduced only to its torsion part.
It means that it's not 0. L in general is the integer.
It is
It's a
integer.
positive integer.
Yeah,
Or
positive
and
of 0. Positive
Means that what you say is positive means that it's not 0.
is not 0. And from here we can prove that if there is one rational point in the curve, there are infinitely many rational points by constructing with the chords, and which means that if we have one triangle corresponding to a congruent number, we have many triangles corresponding to these congruent numbers. So here I skip, and now we arrive to some, we don't know so much about this R. We don't know so much about this R. And the conjecture of Birch and Swinnerton-Dyer is this, that asymptotically, we are going to look at the point is that we wanted to discuss the number of rational points on Q. And this is difficult. So we reduce model P. And we look at the number of the point on ZP for the curve. Something that I call id ZP. This is the set of points in ZP on the curve. I look at the number of those points and I divide by P. And I took some geometric mean. And the conjecture, this is weak form of the conjecture is that this should be proportional to log x of r. That we don't know too much, it should be this. And this is the weak form of the conjecture of Swinnerton-Dyer, Birch and Swinnerton-Dyer. And now,
So what is the C?
some constant that I say this is the weak form, and the strong form is to.
Like in another can be put in proportional when we put a constant in proportion.
Yeah, but this has meaning. What I said is that this number divided by this has a limit. Right. I don't make precise this C. This C can be given explicitly in terms of another complicated text. But for us, what is important, you can that the power, the rank appear here in the power of log x. And this C can be made explicit. So there is another way to understand, to formulate this conjecture here. Another way is to look at things analytically. So what we are going to do, we consider for ZP. So we localize and we work on ZP. We look at the guessed number of solution, which is we look at the error term, sorry, E of ZP. I say that the guessed number of solution is this, and then we introduce the error term. And then this AP, I write it like this. And from this, I construct a kind of zeta function, which is the product of all prime P and 1 minus. And here, I divide PS. Plus and something that P over P to S. Now I define this function. This is what we call the L function of the curve at S. And when you take S equal to 1, you cancel and you take the partial product, you obtain something like this. And the idea is to study the behavior of this analytic function as function of S, and eventually to see, I forgot minus 1. And the idea is study this function is convergent, this product is convergent for your part of S significantly of 2. And this is a big theorem, one of the main theorem that was proved around 1990 in the proof of last theorem, that actually this function extends holomorphically. Expand? Sorry. This product, infinite product, converge only a priori only for this. But it has analytic continuation to all the complex things. This is what we call the consequence of the modularity theorem of Wiles and his collaborator. And it was the main theorem in the proof of last Fermat theorem. So we use the modularity theorem. And this modularity theorem was proved by several people. All the people contributed to last Fermat theorem: Weiss, Conrad, Fred Diamond, Taylor, and Christophe Bray. And the idea is to look not at the elliptic curve in the affine plane, but as Riemann surfaces. And this is the technique of the modularity theorem. Let me just go back to something that I skipped before. The Riemann zeta function. Why, if you take s equal to 1 here, then you will find this product. If you take partial product but at s equal to 1, then you obtain this. So which means that to have information about this conjecture, you need to study at s equal to 1 this infinite product, and at s equal to 1, it is legitimate to ask for s equal to 1, because we say this infinite product has analytic continuation even at s equal to 1. Has analytic continuation to all the complex plane. Then in particular, you can take the value at s equal to 1. But let me look at the first time that the Riemann zeta function or the harmonic series appear is in 1320 by Nicole Doran. And Nicole Doran proved that this harmonic series, written in blue, is divergent by just considering 1, and then 1 over 2, and then he grouped 1 over 3 and 1 over 4, and then he grouped 1 over 5 until 1 over 8, and so on. And each group can be greater than 1/2, 1/2, 1/2. And then he proved that the harmonic series is bigger than 1 over 2 plus 1 over 2 plus 1 over 2 plus 1 over 2, and then this is divergent. So the observation of Nicole Doran stopped here at when I put 3 fat blue points. But now, what we can say is that,
I'm sure that Doran put that in his talk.
yeah, but without speaking about infinity and so on, just formal. Yeah, this is the first. But what we can say is that if you take 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 and so on, but now I keep 1, and then I take 4 1 over 2, and then 6 1 over 2, and then 8 1 over 2, and I found this strange inequality 1 plus 2 plus 3 plus 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 plus. So you started with the blue series 1 over 2 plus 1 over 3 plus 1 over 4 plus, and you find that it is greater than 1 plus 2 plus 3 plus so on, which means that the part is bigger than the total, which is a priori absurd, but it can be understood in terms of analytic continuation, because in the modern string theory, 1 plus 2 plus 3 plus plus is equal to -1 over 12, which make this inequality true. In any case, this observation 1 plus 2 plus 3 plus 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 infinity was showed by Ramanujan to Hardy. And Hardy was shocked, but he found proof by analytic continuation. This means that the harmonic series, which is the value at s equal to 1, contains a lot of information, and this is exactly what happened. What happened here? So, because time is going fast, I'm going just to give you. No, but we started with 10 minutes late. Yeah.
You don't want to be a philosopher?
No. I wanted to be, but just I want to let me just finish this L series. Here we are using the strong theorem of the theory of elliptic curves, this L series has analytic continuation to all the complex plane. Then we can speak at the value at S1. And now I look at the Taylor expansion of this as equal to 1. And then I can always write it as S minus 1 of prime. I didn't say that R prime is positive. It could be 0 plus higher order term. Now, because this series has analytic continuation at S equal to 1, we can speak about this. And now, the beautiful Birch and Swinnerton-Dyer conjecture is that this analytic L prime is equal to the algebra R. Algebra and analysis meet, and we have this. So this is really deep, that their congruent numbers are related to this kind of beautiful theorems. And we have some criteria of Turner that n is congruent number if and only if the set of triple x, y, z such that 2x2 plus y2 plus 8z2 equal to n is twice the number of triples such that 2x2 plus y2 plus 32z2 equal to n. And here I gave example for 41. Test that 41 is congruent.
Sorry, we know, perhaps it's implicit in what you say that you not grasp it. But we know how many congruent numbers there are.
We know the density. There are infinitely many, and we know the density. In my paper to go to the conference, I gave the precise statistics of that.
I did not read
So I gave
we know that there are infinity.
Yeah, and we know the density.
We know the density.
Yeah, it is written in my paper. And here, and I wanted to finish that in this paper that I submitted for the conference, there is an appendix written by my friend Bill Alambert, who is a very expert in computer algebra, and he wrote an appendix in that paper. And with this paper, we can construct so many things with the congruent numbers. So this is the story that I want to tell you. Congruence number coming from 1930 something to today, and why Al-Azan Ibn al-Haytham considered this number. I don't know why. What kind of link between geometric optics and this congruent number? This is I don't know. And how he obtained is by physical argument, by optical argument, by I don't know. In any case, the Birch and Swinnerton-Dyer is considered as one of the 7 millennium problems, like a human hypothesis, or like Young-Mills or Hodge conjecture, or other conjecture. So I stop here. Thank you very much.
Let me talk. The number, I like
The congruent number, we call them.
So they are all congruent numbers? No.
The sequence that I gave, yes.
All of them are
Yes, but not.
but
But
157.
yeah, no. This is just example of congruence. Maybe he didn't give all the list between this.
So it's not in order.
No. Maybe he missed some. And
He
one
missed some.
specific.
Okay. So the question is then the following: you don't know how Al-Haytham arrives at this.
No.
I think that is impossible to know, neither for you.
No,
for any other
because
one.
so many.
But where? So my point is the following: you introduce the notion of congruent number in a very simple arithmetical way. You use the triangle, but the triangle is not trivial. So the definition of congruent number is trivial. Not trivial, it's simple. But then you use a congruent number for giving a very sophisticated theorem in in algebraic geometry.
Yeah.
So one can ask why you are interested in congruent number, because the definition that you gave in congruent number, you can give another similar.
Yeah.
Why exactly this? If you don't know a priori, if you know a priori that this number give your result in algebraic geometry, so you understand why we are interested in this number. But before knowing this, why someone should be interested in a congruent number if simply you define a congruent number by their arithmetical definition?
But maybe,
for example, in the arithmetical definition, you say 2 the square of triangle. So you have 2n. You could put 5n. So why you put 2n rather than 5n or 7n or 27n? Why?
I can't answer this question. It is like for tabit number. Why you ask that m should be the sum of the divisor of n deep less than n?
What make congruent number intelligent in themselves, independently of algebraic geometry?
But it is enough that algebraic geometry. You know, for instance, if I consider Sirac, let me finish. Yes. If I consider Sirac's conjecture, that you start from n, and if n is odd, if n is even, you take n over 2, and if n is odd, you take 3n plus 1, and if you continue this process, and the conjecture is that you will arrive to 1. Mm-hmm. This is not proved yet. Here, I don't see any theory behind this problem. This is a difficult problem, because if you take n and you continue it, easy.
So I think that you did not grab my question. Of course, the fact that you have the development in algebraic geometry may congruent number interesting. That's, of course, that is not my point. My point is that this development in algebraic geometry, of course, they could not be known by Fermat or by Lanzan. So they are discovering in the last century. So why people before that was interested in congruent number?
But maybe it is for some geometric optic reason that we lost.
Okay.
That we lost.
We have no idea.
No. But you know, I can also tell you that the interested all those people around 1,000 years, it is enough to consider them as very, very serious.
That's exactly the question.
I'm telling you, maybe there is some question of astronomy or maybe of optics. You know, Aladdin is considered as really the father of geometric optics. He brought a lot of theorems, and maybe there is some that this is the work of the historian. You know,
we should ask to Rachel.
Yeah, the historian. Yeah, this is very important, and there is now, and also is Frederick to consider this question is very important for me. It is kind of argument.
Other question.
I don't know. You could also consider that thousands, if not millions, of sequences of numbers have been studied. Look at the online sequences, encyclopedia. And this one turned out to be important, because later on there were interesting results. All the other ones disappeared. Yeah, we don't. It's possible that some other sequence in the future will become important because it will solve Birch and Swinnerton-Dyer. I'm not an expert in number theory, so whatever I say is relevant.
I'm not expert in normal theory or neither, but my interest was in that. I said that the curve here, the curve y2. I was interested in this curve for many reasons. If you take, for instance, the lemniscate. Let me go back. And you wanted to compute the length of an arc of the lemniscate here. So the period, it is a question of the period. The period for the circle you have 2 pi, but for the lemniscate is given by this integral. They give by this integral, and this integral is related to the curve for x3 minus 1/4 of x and y. And here you have congruent number apparently.
But sorry, let's get back to the congruent number. If you take a Pythagorean triple,
Yeah.
you have 3 natural number, integer number that satisfy the first condition. So insofar the integer, the product is a natural number.
Yes.
I don't know whether we can be sure that it's an even number, but I suppose that it could be an even number. So if you have A, B that are part of the Pythagorean triple, such that the product is an even number, so the alpha of this number is certain congruent. Correct?
So here I have theorem, and it's congruent number if and only if there is 3 rational square in arithmetic progression.
Okay, but forget the rational, take only the integer.
Yeah.
So you have an infinity of Pythagorean triple. Okay? So you take one of them, n and m, n, m, p. And then n and m are integer. So n times m is certainly an integer too. It could be a odd integer. In this case, you have nothing, but it could be an even integer. And in this case, the half of the even integer is a rational number, a congruent number.
Yes.
So to prove that there is an infinity for congruent number is enough to prove that there are infinity of Pythagorean triple that such that okay. And it's true that there is infinity of Pythagorean triple.
Yeah. And from each Pythagorean, for each congruent number, you can construct a. Yeah.
And out this question that you say, is there a connection with White's proof of Fermat conjecture?
This is exactly what they say when they say that this product, infinite product, has analytic continuation to all complex plane. Yeah. This is the modularity theorem, and the modularity theorem is the main ingredient. I gave the names. Here, I say twice in the top.
The White.
Yeah.
Analytic continuation.
Yeah.
And this is a lemma for the Fermat.
Oh, not only the lemma. This is one consequence of the modularity theorem. What is the modularity?
The Fermat is a consequence of this.
This is consequence of what is the modularity theorem? Look at this picture here. So, we consider our elliptic curve.
Yeah.
So far, I consider it as just on the affine plane with x and y. But now you can consider it in C. And then it is, and you add some point at infinity. And then you obtain what I put here as Riemann surfaces. Then we change the plane. The point is that this infinite product here that I wrote is something related by what we call millennium transform to a differential form in this here. And here I put, you know, if you take this and you use the uniformization theorem, then you have a group acting on the upper head plane, such that the quotient of the upper head plane by this group will be this Riemann surface. This is the group. And the modularity theorem is something that related this with a called a Dirichlet series, L series. Theta function, if you want, to put the series, which is some kind of differential form on the surface. The modularity theorem link, this is I call algebra plus geometry plus analysis equal to arithmetic in the title. The modularity theorem is that this is related to modular form, and modular form is some kind of differential. So the technique of Wiles are really very present here.
Number theories.
No, this is Wiles. This is Wiles and his students. You have to say that Wiles was student of Coates, and Coates is the one that he found the manuscript of Alazen at the French National Library.
Coates,
John Coates.
John Coates.
Yeah,
The editor of the computer. John Coates, the English mathematician of the
Australian.
no, please, another one. So
John, yeah.
Okay.
He passed away 2 years ago.
Okay.
He was the advisor of Wiles, and Wiles is the advisor of that's the people.
Additive.
Why it's AQ.
Stop to call me doctor. Even professor. I'm Mark. Point. Okay.
Yeah, so a square plus b square equal to c square, and ab is equal to 2 and y naught 5 and 3. And what I have observed while you were saying is that if you write like a cube plus b cube plus c cube is equal to d cube and abc equal to, then you can see that product of a, b, and c will always be a multiple of 3.
Write it.
Yeah, please tell me.
So the congruent number is like.
Yeah.
What I'm saying is that in general, you can say that 2 m numbers equal to some x square, then the product of all these numbers will be a multiple of m. And I think that's why it has got that specific properties.
And this is a theorem that
You proved it or is not?
No, that's what I put some numbers, and that's what I
don't
found.
see how you can get ATC, the product of all this.
An example is like
We have a neural manager here.
I'm still confused with here. What you put here? 2?
oh, that's any number.
And here, this power here.
Oh, sorry, it's m.
It's the same there.
Yeah.
M plus m plus c m equal xm. And then if you have the product of that, so what is the m, the index m there?
Oh,
So
this
you
means
have
M numbers, like here we
M
have
number.
3.
Okay, you have M number.
M,
Okay.
M number. I have to think, I don't know.
And I don't know how to prove also.
Yeah, but
not-
we have to make sure that it is at least numerically true.
And that is for your report for you have to prove this theorem. This would explain why this is interesting, of course.
Maybe. I don't feel.
So yeah, this is 60. That is equal 3 times 20, and 3 plus 4 plus 5x 3. And you tried it on different cases?
No, I was trying actually. Like while you ask the question, only it's trying me so.
So it means that in this case we have 2, and so the product is a product of 2, and so it means that all. So if ABC is a Pythagorean triple, the product AB is always even. Is what you say.
Not even, like it will be a multiple of that power.
Yes, 2.
Yeah, that's what I first said, because I was wondering if it can have like 2 sides equal for a triangle, then that can generate a congruent number. That cannot generate because it will have root 2, it's a rational number.
So, and that this would do a Pythagorean triple, and so this would explain effectively why. If it were really true, would explain the interest of the complete number independent of the own job. Very nice, very nice. I hope that is true. You have to prove it for the report of the same, okay?
For the next thing.
But when you know that when Ramanujan wrote to Hardy, Ramanujan wrote to Hardy and said to Hardy, he wrote to Littlewood, in fact, Little Second. And so then Ramanujan wrote again to Littlewood, if you remember well the story, and Littlewood went to see Hardy, and I said, but this is not so stupid, that is fantastic. What is that? So, let me ask him, do you have proof? And Ramanujan said, proof? What are proofs? That is true. You need a proof. Proof. And in fact, it was true. Not true. No one of them was false. But he never thought that he could have given a proof.
I can stop there. I can stop there.
Okay, other questions?
I don't know how to
So
stop.
thank you. Thank you, Ahmed.
Okay.